Good morning, good afternoon, and good evening to everyone. We have very international audience today. Welcome to this new video webinar. If you are one of our partners or one of our new partners, welcome to the WIDIA team. And also if you're one of our customers or just someone who is interested in this webinar. My name is Isabel Milan and I'm from the WIDIA marketing team. So today we have a great presentation. It's on machinability of workpiece materials, and we're also going to show you how to select the right cutting tools. I've seen this presentation, it's really complete. You will find a lot of things covered, so we hope that you enjoyed it as much as I did. We have Ramesh, who is one of our new presenters, so please encourage Ramesh. This is the first video webinar that he has a lot of experience in webinars, but it's the first video webinar for him. He's our technology manager, and he has a lot of experience in powder metallurgy and manufacturing. Before we start, I wanted to say a few words on safety. Safety is very important for our organization. So please make sure that you are in a safe environment. If you are also in the office or in a building, make sure that you check where the emergency exits are. And if you are in the car, we advise you to stop so you can better follow the webinar. We are using the GoToWebinar tool where you are not able to speak, but you're able to write to us and ask us questions by using the control panel. So if you find the questions section in the control panel, feel free to ask any questions there. And while Ramesh is going to do the presentation, whenever you feel you have something you want to ask him, just write it there. We will answer all of the questions in the Q&A session at the end of the webinar. A few last things, make sure that you follow us also on our YouTube channel and our other social media channels, because we publish a lot of nice videos, information about products, machining tips, and also our next webinar. So I think that is all. I will leave it to you, Ramesh, for the webinar, and enjoy to everyone.
Yeah, thank you, Isabel. Can you just confirm I'm audible and my screen is visible?
Yes, Ramesh. We just need the full screen.
Yeah.
That's perfect.
Okay. Okay. Thank you, Isabel. And good morning, good afternoon, good evening, everyone who are participating in this webinar. Myself, Ramesh, and I will take you through this topic of machinability of workpiece materials and cutting tool selection. So as all of you know, some of you are already into metal cutting process, or some of you into manufacturing of some of the components using this material. Maybe some of you may be into cutting tool area. So as a machining is concerned, we classify these workpiece into a different 6 categories. And these are the categories what you see as an ISO nomenclature. It's a PMKNSH, and they're classified due to the difference in its characteristics, in the way in which it behaves during machining, and what are the tool selection, machining parameter, how the tool material need to be treated as a machining is concerned. So hence they are classified under these categories. So in the steel, okay, we covering P1 to P6, a different type of steel which has a different composition, different properties. Stainless steel, M class of material, is M1 to M3. Again, there are different type of stainless steel. K class of material is a cast iron, is K1 to K3. In non-ferrous, we will understand what you mean by non-ferrous and how the machinability is different and what we need to do. It's a N1 to N7. Yes, super alloys, they are typically the high temperature alloys used at application which require a high properties or high strength at elevated temperature, S1 to S4. And finally, the hardened material which are hardened to enhance its strength, and it require its end application H1 to H4. So these are the 6 class of material, and we will understand certain basic properties and then see for each material and how the properties are related and how we can select the right cutting tool and cutting tool conditions. So we are not getting into any of the metallurgical characteristics in detail. We look at only which are easily understandable. But if you have any specific questions, put it under chat. If you're able to answer, we'll answer. Otherwise, I will come back to you with a right answer. So from the catalog, you can also see that the cutting tool selection is also based on the level of machining. That is what the number stands. The P stands for steel here, or M for stainless steel, or K. Then last two characters or numbers 0, 1, 2, 5, 0. It defines the complexity of the machining application. Is it a finishing or is it roughing? So P01 for a finishing where the material is very hard, less of interruption. Your cutting tool should be very hard, wear resistance. As number increases, move from 01 to 30, 30 to 50, where you have many high level of interruption or varying depth of cut, or is a rough surfaces where your tool should have a good toughness. So you have one is class of material, the second one is the application range, whether the machining is smooth or it will have an interruption or impacting the load involved in the machining process. So moving to the next topic is on the material and impact on machining. So why are these 6 class of material groups are important? Why they are classified as 6 different groups? And so the reason for this is that the workpiece materials are really effects in selection of the tool. So because some of them are because of its composition, or is because of the way its component is manufactured, or the way the component has a shape, is it a material has a work hardening nature? So many reasons, and we will learn during this process. And so that characteristics decide the selection of whether what lead angle you have to consider, what is the rake angle, positive or negative, relief, edge preparation, how strong edge should be, is it should be sharp, or it should have a rounding, or it should have a T-line, and what is the grade and coating I need to select. Is it a tough grade or hard grade or in alloy grade, CVD, PVD, what type of coating I need to select. Okay, the entire tool selection is defined by the material characteristics. And second important feature is on the chip forming. What type of chip it is generating. Is it a continuous or is a short segmented chips? So now the machining industries are moving toward from a manual process to a completely automated and interlinked. So now if you have a complete chip breaking process, chip forming process, you need to have a control mechanism how to handle it. So the chip forming is one of the key feature in selection of the tool. And the last one is the operating conditions. Now I had to compromise between the tool life and the productivity. If I need a high tool life, maybe I had to compromise on my productivity because I had to run at a low cutting speed or lower parameter. Now my entire process chain is linked with respect to the time involved. So then I had to increase my parameters, the high speed or higher feed, but it may compromise on tool life. And also they are not linear. I will show one of the graph, they are not linear. So now I had to balance between the tool life and productivity. That selection of the machining parameters are influenced by the component and the material. So now when you say we had a topic itself is on the machinability, right? Now what is meaning of a machinability? So in the simple term machinability, I just define it as a ease at which material can be machined and is commonly represented as a percentage. So here it talks about some kind of a subjective word, right? Ease at which material can be machined. The ease can be different for a different user. For someone it is a good machinability, means it gives a good surface finish, so that RA of less than say 0.4 microns, so that I don't need to do the secondary operation, I don't need to do the grinding, I don't need to do any of the extra work. So for someone else it's a high tool life, so that the tool change time over can be reduced, so that I have a high utilization of my equipment. For someone is about productivity, how fast I can complete my component, so that can I run at a very high speed, maybe 600 meters per minute, so that my cycle time is reduced. So time is the money. So it is different for different. So but from the American Iron and Steel Institute, AISI, they have a certain guidelines. They use B1112 cold rolled steel. It's a low carbon steel with 0.12% carbon, which has a 160 BHN hardness. This is used as a reference. and it is defined machinability of this material as rating 100%. That means that is a reference. And for the rest of the material, so as shown here at the bottom of the slide, how the machinability rating of any other material are estimated. It is a ratio of speed of machining a workpiece at which gives a 60 minutes up to life divided by the same life achieved for B112, the parameter or speed at which you run for B112, and you get the 60 minutes up to life. So if I go by some example, if I run at say 200 or 300 meters per minute for a B112, if I get a say, 60 minutes of to life, and if I'm moving from B112, I go to SAE 4140 material, and to get the same 60 minute of to life, maybe I had to run at say 150 meters per minute. And now the ratio of 150 divided by 300 is a 50%. That means the machinability rating of SAE 4140 is 50% of B112. That is with respect to the speed at which I'll be running to achieve the same life. So that is a template used to define the machinability rating of different material with respect to B1112. So it is the machinability rating of all the materials are affected by. There are four major properties of the material. One is a ductility, hardness, thermal conductivity, and composition. Okay, we will look at this individually and how it influences the machinability. So I defined initially that machinability is always the ease at which it is machining, and the ease of machining is quantified as these four parameters. One is a power consumption. So can I run at a condition where my power consumption is least, my utilization of equipment rating is least? Can I run at a very high cutting speed? Cutting speed is a second metric. Third one is surface finish. Can I get a good surface finish? So that means the material has a good machinability so that I don't need to do the secondary operation. Can this workpiece can give a high tool life, less tool wear, so that I can reduce my tool consumption. So these are the quantifiable parameter used to define the machinability of a material. And this is a simple chart and is only a reference because it is also influenced by the component type and the shape, and the surface characteristic of the component also determines the machinability rating. But in general, for a similar type of a component, so B112 has taken as a reference 100%. And as I given an example previously, if you go to SAE 4140, its machinability rating is 66%. That means you have to run at a cutting speed 6% of B112 to get the same tool life. Okay, this is a simple chart, and you might get it in many of a cutting tool manufacturer catalogs, or it will available in the open source. And this can be starting point to fix the machine condition, and then further you can work on optimizing to meet your product characteristics or product CTQs, and also balance between the tool life and productivity. Okay, so now we talk about machinability is mostly defined in terms of the cutting speed. Now, what is the role of cutting speed in a simple term? So this is a cutting speed of 3000 surface feet per minute. The typical tool life is 10 minutes. And as you reduce the cutting speed and you go to the 500, it is 1/6 or of 300 SFPM. And you can see that the tool life has increased by 100 or 110 minutes. That is increased by 11 times. So even though speed has dropped by 1/6, the cutting the tool life has increased by 11 times. So there is a even though there is a relationship between the tool life and the cutting speed, but they are not linear. So why this is a difference in the life with the speed? As the cutting speed increases, the increase in cutting speed generates more heat, and more the heat is generated, any material when it is heated, it loses its wear resistance, and with the application of a cutting force, it could deform or it could wear out faster, and that's how it decreases the tool life. And as you decreases the cutting speed, so it reduces the heat generation during the machining process, and that's how you're able to get a increased tool life. This is a thumb rule. The rate at which it increase or decrease in tool life with respect to the cutting speed again depends on the workpiece, and also depends on the tool you selected. So what type of grade, what type of coating, what type of geometry. But in general, the increase in cutting speed reduces the tool life because of the heat generation. Now, can we link all these basic knowledge into the properties, 4 properties, which are critical in selection of a tool material or tool machining conditions? First property is a ductility. Ductility, by definition, it's a basic what we learned in our schoolings, is a measure of how much a material can be plastically deformed without a fracture. That means you are able to elongate a material. So more the elongation before the fracture, it is more ductile. So this is a simple test in the test specimen, the standard test specimen in using in UTM. You do the test, and this is how the component looks, but actually it has a particular shape and profile. And the picture A shows is kind of a brittle fracture. You can, when you apply a tensile load, it will break and into 2 pieces without much forming a necking. As the ductility increases, you move from picture A to B and C, you can see that there is an elongation of the component before it fractures. The similar phenomena or behavior happens during the machining process. When the chips are formed, depending on the type of the material, is a brittle or semi-ductile or a highly ductile, the chip formations goes in this pattern. Now, what happens when the material is highly ductile, right? So if you refer this picture, you get to know when the material is highly ductile, the chips forms are continuous. That means it's a continuous elongated chip. Just imagine the material like aluminum. So it's a highly ductile material, is a continuous chips forms. You need higher cutting force to break the chips, because you know that any soft material, you will think it's a soft, but if you want to cut it, you can't cut it. You need a sharp edge, or if you try to pull it, it will tear away. You'll get a poor surface finish. So that means you need to have a high cutting force to make a ductile material to have a good chip breaking. And materials are very low in hardness. You don't need high cutting forces. I mean, you don't need a high load to make it cut the material, but to break the chips, you need a high cutting forces. So, and what is the other side of it is a low ductile material. Imagine a cast iron. It's a relatively a brittle material. It forms a segmented chips, short chips, something similar to picture A. It breaks into a fine chips. If you see in a machining process, there are a lot of powdery chips, and it has a lower cutting force with respect to chip breaking, because it easily breaks the chips. You don't need to apply a high force to break the chips, but it have a high hardness. It may require certain other tooling selection to take care of the high hardness of the material. So the hardness and ductility are inversely related. Typically in the metal which are very high hardness have a low ductility, and hence you have a short segmented chips. When the metal has a typically low hardness, will be ductile, and it will have a long continuous chips, and you require high cutting force. So the second property is a hardness. So hardness is a measure of material's ability to resist deformation. That means the picture shown here, you have an indenter, you apply a load, and how much material penetrate, and it is an indication of the hardness. More the penetration, more the deformation, lower the hardness, and lesser the higher the hardness. Okay, so that is a level of penetration. So that means when you are applying, when you are cutting a component, if you are to remove a say 1.5 mm depth of cut, you have to apply the force required to penetrate 1.5 mm, right? Harder the material, you need to apply more force to penetrate for 1.5 mm. So softer the material is a less force. So it is directly, the hardness is influences the cutting force during the machining process. So as the hardness increases, I've given an example, right? So cutting forces are directly proportional to the hardness of the material, because you have to plastically deform the workpiece to cut it. So more the hardness, more the load you have to apply to remove 1.5 mm depth of cut. So when you apply more force, more is the heat generated during the machining processes, and the more the heat generated, so heat is transferred to the tool, and it loses out its hardness and wear resistance. Tool life decreases. So as the hardness increases, more heat generation, lesser the tool life. And yeah, so higher the hardness, so lower the tool life. So third important characteristics is the thermal conductivity. By definition, it is a rate of heat transfer through a material in steady state, and how the heat is transferred from one end to the other end of a component, right? So if you see the convention, this is a typical picture or by the simulation what we can see. So when the tool is cut, it is a shear zone, and the load is acting on the shear zone, but the heat is generated in the shear zone. Along with that, the heat is also generated at tool chip interface. It's around 704 degrees centigrade, depending again on the workpiece material, composition workpiece. Now, what happens when the thermal conductivity is low? It retains the heat in the shear zone. That means whatever heat is generated during the machining process, it is retained at the where the temperature is generated. It will not dissipate either through the chips or through the workpiece. It will be retained or concentrated in the shear zone or in the tool chip interfaces. So it resulting in premature heat deformation of the cutting tool, because the heat is concentrating on the tool surface. It is not dissipated through the chips on the workpiece, and it is passed on to the tool, and tool wears out faster, either deformation or by the wear. Whereas on the other side of it, when the conductivity is high, or whatever the heat is generated, because workpiece has a good conductivity, the heat is either transferred to the other part of the workpiece or it is carried away by the chips. It's carried away by chips instead of forwarding, passing it on to the tool. But there is a other issue. It is good from the tooling perspective. The heat is not transferred to the tool, but can lead to part distortion, because the heat is workpiece has a good conductivity. The heat is transferred to the workpiece. So depending on how rigid you are holding it, because of the high rigidity and how high the clamping pressure, the component could distort, and we have a mechanism how it can be controlled. We'll cover that. So it's just to summarize. So when you have a low thermal conductivity, lead to low machinability, because heat is not properly dispersed. It is concentrating on the shear zone or the tool chip interface, resulting in faster tool wear. And in some cases, when the materials are gummy, which are sticky, it can also lead to built-up edge formation. That means the workpiece will stick to the cutting edge of the tooling. So this is the behavior of a low conductivity material. And the last important characteristics or a parameter contributing to the machinability is the composition. So there are elements which are deliberately added to the workpiece to make it the machining easier: lead, sulfur, phosphorus, calcium, magnesium oxide, and selenium, something like that. So how they help? Some of them, lead and sulfur, they form it's kind of an intermetallic at the grain boundary, making it to break the chips. It helps in breaking the chips so that you don't need to apply high cutting force. And some of them, like sulfur and magnesium oxide, act as a lubricant. It reduces the friction, where we saw in the previous picture that the maximum temperature is the tool chip interface because of the friction. And if these component in the workpiece reduces the friction and reduces the heat. And some of the example is AISI 4340 steel, where phosphorus and sulfur are added as a machining aid. It helps in removing, improving the machinability. There are other elements which are added to enhance the characteristics or properties of the workpiece to suit its end application. And these are commonly used are chromium, manganese, molybdenum, nickel, and all this listed here. And the example are like a super alloy material, which is either a cobalt based or an iron based, which has a high strength at elevated temperature. It is good for end application. It is needed, but as far as the machining is concerned, it is poor, and it will be the machinability rating in the order of 30%, 40%. So one of the reason is this composition increases the strength even at elevated temperature. Second, it also makes the material gummy or sticky, and also it's a ductile. The third one is some of the elements also makes the workpiece work hardening. That means as you apply cutting forces, surface becomes harder, and if you're doing a multiple passes, it can lead to build up depth of cut notch formation. So there are elements which aids machining. There are elements which makes the machining more difficult. So these are the foundation for moving to each material in the subsequent slides. So remember about four parameters of the workpiece. The one is the hardness, the ductility, and the thermal conductivity, and the metal composition. So these are the four things decides what selection of a work tool material and the machining conditions. Okay, so these are some of the example. So manganese, chromium, molybdenum, nickel, vanadium are added in the workpiece for different reasons. So they are needed for the product component end application is required. Either improve the wear resistance, improve the toughness, improve the grip resistance. Sometimes it also helps in making it ductile and all forgeable. So all these characteristics are improved by these along additions, but definitely has a negative impact on the machinability. So now this is the first slide which I have shown. These are the 6 class of material. What we will do now is we'll go through all these 6 class of material and maybe some uses, because that I will not cover much on the usage of it because it's already known, and look at the basic properties of these material and how the selection of the machining condition based on the material properties. So this is, we already discussed material. What material is being cut is the first thing. So now I know my component has a certain material. It's a low carbon steel, alloy steel, stainless steel. Okay, what material is being cut? Now can I look at what are the properties of this material? Probably so many of a user, if you are using a material in your machining shop, you will have a material test certificate. Or if you're all using it for a long time, you know what are the properties? What is the tensile strength? What is the hardness? Or what is the composition of the material, and is that any alloying additions present which is make machining more difficult. You're seeing that now cast irons are added with some other elements like nickel and copper, which makes it more difficult. So you get to idea of, okay, what is your component, what is the material composition of your component, and based on that you can refer to the product catalogs from your manufacturer. So they will give all the compositions and certain properties along with your test certificate from your suppliers, and you can categorize under with as a PMK NSH category of material. Okay, so let's start with steel, because the steel is the one which contributes almost 50% of the total material consumption in the world. And by definition, any material is iron-based material which carbon content is less than 2.1% class comes under a class of steel. And it is always processed through either through hot forging, cold forging, and is also sometimes through the casting route. So there are different type of steel present. Either is a carbon steel or alloy steel. Carbon steel or plain carbon steel where the alloying additions are less than 3%. Alloy steels are alloying addition deliberately added to the different percentages to enhance its strength depending on the end usage. The plain carbon steel, desulfurized manganese, nickel chromium, molybdenum, yeah, different type of steel. Okay, there are some of the pictures of the component made out of steel. Now, what are the properties of a steel? Okay, we looked at P1 and P2. It's a low carbon, medium carbon steel. They're all typically in the similar nature. So maybe each material will have a different machining condition, but we trying to group it here so that it'll easy to understand. They're all low carbon. That means they're all soft and gummy because of higher iron content, less carbon. So less of a hardness in this material. And because of its soft ductile, it is a long chipping, and the chips are difficult to control as it becomes long. Torn finishes, because any material which are not easy to break the chips, it will lead to torn finish, so poor surface finish, and resulting in the burr. But it have a good thermal conductivity because composition contains mainly iron, and it has a good favorable machinability up to 100% of the references. So this is a simple strength diagram. It is around, say, 400, 420, the tensile strength of this material. Now, we know this is soft and gummy, good thermal conductivity, and it is difficult to machine considering the chip formation. How the selection of tool material? We need to have a tool which are positive rake so that you reduce the cutting force, because this has a long chipping. So you need to have high cutting force, which can be reduced by having a positive rake. You can run it because the low hardness is low, so you can run it very high cutting speed. Since it's soft and gummy, so you may have to watch out for built-up edge formation. So that's why you are looking for a positive insert. You can have an alloy grade, so that since you are running at a very high cutting speed, alloy grade have a high hardness at elevated temperature, is suitable. And most of the tooling for steel and cast iron machining and stainless steel machining are with the CVD MTTSEN coating with aluminum oxide, and use of coolant recommended to handle the chips. Even though it has a good thermal conductivity, the coolant will help in controlling the chips or breaking the chips. Okay, so this is both for P1 and P2. As you move from plain carbon steel to alloy steel, any alloying addition, like here we are talking about alloy steel and a tool steel with the two different hardness. Any alloying addition, it loses a certain inherent property like conductivity. Any alloying addition reduces the conductivity because you are replacing iron by some other elements. And if you look at the alloying addition, they're all either with chromium, maybe little increase in carbon, nickel, molybdenum. They're all good. They enhance the strength. If you look at the system diagram, you can see that it can go as high as 1700 MPa tensile strength, and with a lower elongation. So there more becomes more high strength, high abrasive, and also during machining, because they are a little relatively harder, so you get a better surface finish because chips are will be smaller, and greater tendency to work hardening, because any alloying additions, it reduces the conductivity. And high strength and low conductivity is the worst combination, because when the cutting forces are high, a lot of heat is generated during the machining process, which is not taken away from the tool chip interface or a shearing zone, make the material little getting harder, getting heat treated, kind of a heat treated. So it makes the surface harder, and that's why it has a lower machinability. So now how the selection of a tool, because of a high strength, work hardening nature, lower or medium thermal conductivity, how my tool selection should be. Because of a high strength, high hardness, you need to have a negative rake so that you strengthen your tool, otherwise it can lead to breakage. And you reduce the cutting speed because the conductivity is lower, so you need to have a less of heat generation so that the tools are protected. And use a alloy carbide substrate because you need to have high temperature hardness for the cutting tool point of view. So use the alloy carbide with the CVD, TACN and aluminum oxide coating. Increase your edge preparation. That means you have a edge rounding or honing of say 50 microns or 60 micron to make it stronger. And use of coolant is a must because your cutting force is high, a lot of heat is generated. Second one is your conductivity is medium, so the heat will not be dissipated. So one way of dissipating the heat is by use of a coolant. Okay, that's how you select the tooling for alloy and tool steel. The third type of material is a stainless steel. And as you know, stainless steel is a different class of material because of its composition. And typically, any material which contains more than 10.5% chromium classified as stainless steel, and they have a lower carbon content at 1.2% and less. And that's how it is. Sometimes it's difficult to heat treat as well. And it can be processed through forging and either hot forging or cold forging. Also, sometimes extruded, and it will have a higher strength compared to alloy steel or stainless steel, low carbon steel. So stainless steel will have a higher strength compared to carbon steel and alloy steel. And this is just one of the representative stress strain diagram for stainless steel, and it can go high as high as 1200 MPa. The more important thing is you can see that the effect of work hardening as it is during the forming process, the metal getting hardened, it enhances its strength. So similar thing could happen during the machining process. During the machining, because of the cutting forces and because of the heat generation, the workpiece can become hardened during the machining process. So these are some of the components. It's mostly used in the process components and where you require high corrosion resistance. And there are different type of stainless steel. Martensitic, which is a very hard stainless steel. Austenitic is a high strength, high ductile stainless steel. So they have a different selection of a tool machining conditions. So let's get into some of the stainless steel types. First one is a P5 to P6, which is a ferritic and martensitic stainless steel. So as this is used mainly in the chemical industry, food processing industry because of its corrosion resistance properties. And in terms of properties, they're brittle and stringy because the martensitic stainless steels are they're hard, and because of the martensite phase, martensites are typically very highly abrasive, and it is brittle, and it requires high cutting force because hardness is directly related to the cutting forces. And all the stainless steel are lower thermal conductivity because its iron is replaced by chromium and nickel, and they have a high work hardening nature. So the low conductivity, high strength, always leading to a lot of heat accumulation in the cutting zone, making it material subjected to the kind of hardening, heat treatment and hardening. So they have a very poor machinability in the order of 20 to 60%. You can see that 20% is very, very low compared to 100% of a reference steel. So now you have a low conductivity, high work hardening, high cutting forces, brittle. So how the selection of a tool? So now we need a steel grades which geometries of 0 to 10 degree relief, so that you have some strength. We need to have a tool with a good edge strength. Maybe edge rounding should be fairly 50 to 60 micron range. You run at a moderate speed. That's what the Machinability rating suggests. And use an alloy grades because you need a hardness at elevated temperature. Alloyed carbide will have a good hardness at elevated temperature. And the use of a coolant is a must when you have a material which has a poor thermal conductivity. Okay, so you can avoid the work hardening, and you can probably reduces the tool wear because of heat is carried away by the coolant. So the next class of a material is in the stainless steel is austenitic and cast stainless steel. They comes under M1 and M2. They are much more difficult than the martensitic stainless steel because they have a long chipping, tough and stringy. Even the chips, even though it is high strength, it is having a little high ductility as well, makes it a long chipping material. And they are gummy due to presence of chromium and nickel. and they have a lower conductivity similar to a martensitic stainless steel, and this also work hardens rapidly. High strength, low thermal conductivity. Always remember, the material tends to work harden, and hence they have a lower machinability. So that selection is similar to the previously mentioned of martensitic stainless steel, except that it requires much lower cutting speed, and you need a good chip breaking here to take care of a long chipping and a tough stringy workpiece. The chip formations are long. You need a very good chip breaker, and so that you can break the chips and reduce the work hardening process. And use of a coolant and a very little edge preparation is requirement here. So in some cases for austenitic stainless steel, also because you need a low edge preparation, maybe 25 micron hone radius, CVD has some limitations. You can also try with the PVD coated grades, which will be useful for the machining of austenitic stainless steel. But the use of coolant is a must because of a poor conductivity. Duplex stainless steel, and it's a combination of a ferritic and austenitic microstructure, and it is much more difficult because your microstructure has two phases. So one is a hard and one is a very soft, or one is a high strength, one is a soft. So it requires much more difficult to machine because of a combination. Is something like imagine like a composite, so it is becoming more difficult to machine because you have dual microstructure. It has a very high strength, again because of the similar behavior, and obviously that has a low thermal conductivity because it's a composition can continue to have high nickel and chromium, and work hardening always associated with low conductivity, low machinability. So it is your cutting speed will be lower than the austenitic stainless steel, but your other tool selection will remain the same. You need a positive tool rake. You have to reduce the cutting speed to say maybe 80-90 meters per minute to take care of the heat generation and work hardening. You need to prefer to go with aluminum oxide based coating so that it is backed as an insulator. And if you have a low cutting edges, maybe 20 microns edge preparation, so then you have to go for a PVD coating, and flood coolant is what necessary here to avoid the work hardening behavior during the machining process. So just to summarize on the stainless steel category, so work hardening, cutting forces, chip forming, all three are detrimental for the machining is concerned. And there are different type of stainless steel: ferritic based on the microstructure and the composition, ferritic, martensitic, austenitic, super austenitic, and duplex. And if you see that as you go down, it has a unique applications, but from the machining point of view, it is more difficult. As you move from ferritic to duplex, more work hardening nature, so more difficult to machine. Higher cutting forces, you have a lower tool life, and you have a more difficulty in the chip formation. It's difficult to control. So the selection, your tool conditions, tool grades, the cutting speeds are all reduced as you move from ferritic to duplex. The next class is a cast iron. This is the next is probably the second most widely used material, and it is classified separated from steel in terms of carbon content. When the carbon is more than 2.1%, classified as cast iron. And there are different type of cast iron: gray cast iron, ductile iron. It all depends on how the carbon is present in the microstructure and what form. If it is present in the form of flakes, it's a gray cast iron. And if it is present in the form of nodules or spheroids forms, it's called as a ductile cast iron. So look at starting with gray cast iron, and here the carbon content is very high, more than 2.1%. As of all of you know, carbon is a good conductor of heat. So now also it is very brittle because it reacts with iron form in cementite, and it's a brittle phase, and resulting in short segmented chips. So that means it's low ductile. You don't have an issue with the chip formation. Very abrasive, it's very hard, and it's also low to medium hardness depending on the composition. Again, it's a good conductor of heat, and it has a moderate machinability compared to the low carbon steel. Now, how the selection of a tool, because these are hard material, this is an abrasive workpiece material, you need to have a negative rake so that you strengthen your cutting edge, otherwise it can lead to breakage. And also a cast iron are always processed through a casting. You might have a casting defects. To take care of any of the uninterrupted machining condition, you need to have a negative insert so that you give a strength. And you can run at very high cutting speed because it's a good machining in terms of you don't need to break a chips, it automatically breaks the chips. And typically, if you're using a carbide, use a straight carbide with coated CVD coated aluminum oxide. Or if you are running at very high cutting speed, we can still use ceramic and PCBM. And you can use it with the large hone radius to enhance the strength. There are products with the T lands to enhance the strength again. So you don't need a coolant, but with the traditionally it is not required. But now for the last few years, we see that cast irons also machined at very high cutting speed. With a carbide, we go up to 600 meters per minute. Now, so much of heat is generated, so it has to be taken care. Otherwise, component will get disturbed, and also tool count wear out faster. The coolant will help to take away that heat. So otherwise, if you're running at lower cutting speed, you don't need a coolant. But if you're running at high cutting speed, coolant is preferred. So ductile iron is the same in terms of properties, except that ductile iron and compact iron, you can see the stress strain diagram. It becomes increases its strength, reduces its hardness, and also it increases its ductility. Okay, so because the graphite now is not in the form of flakes. Flakes are the one which gives a stress riser, making it brittle. It's moving from a flakes to a nodular, spheroidal shape. Anything round compared to a square or a rectangle, will be more tougher, right? Because it reduces stress concentration, become a tougher. So similarly here, ductile and compact graphite iron become more tougher. So it will be still relatively short segmented, but it is little longer than the gray cast iron. So abrasive, depending on the composition, it have a high strength, and it is harder, but relatively ductile compared to gray cast iron. It have a good conductivity. It has a lower machinability compared to steel of B112, but it is relatively better than an alloy steel. The selection is almost same as a gray cast iron, except that probably you may have to have here the some cases also maybe chip breaker, because it is some kind of a longer chips compared to a gray cast iron. And you can also use CVD coated and the PCBN tools to increase your productivity. And coolant is an optional, but because of the cutting speed, coolant is preferred to take away the heat. So next class of material is a non-ferrous. Any material which where the iron content is less than 50% are classified under non-ferrous category, and they are all low melting, and it's a lightweight, and there are unique characteristics, but it is typically inexpensive because of how it is handled, how it is raw material available, many other reasons. So there are many applications of a non-ferrous material. Aluminum, copper, and all bronze are most commonly you aware, used even in the household applications. So the machinability of this is slightly different from the steel iron-based material. So starting with aluminum, it's a different type: low silicon and high silicon. Low silicon is hypoeutectic, and high silicon is hypereutectic. Silicon makes it abrasive and making a strength for an end application, end component. However, aluminiums are long continuous chips, stringy, which is sticky always, and that's why it is having a low strength. It is alloyed with silicon to enhance its strength, otherwise it will be soft material. And it will have a good strength to weight ratio because it's very light. It's compared to strength to weight, it is a good weight to strength ratio, where there are application where you require a low weight material. You can use this because of its high strength to weight ratio, and its corrosion resistant because there are no iron present. So it's a free machining, easy to cut, and of course it has certain element of edge selection requirement, tool selection requirement, but relatively easy to cut, less cutting forces, very good thermal conductivity, and very good machinability. Now, how the selection of tool, long and continuous chips, as I said, it is up to certain level, it is easy to handle. Beyond it, it is much more difficult. I'm not showing a picture here. If you see it in the open source, you can see that how the chips are formed, very difficult to handle. That's why you need a tool which are very sharp and high positive rake, so that you can cut the chips, you can handle the chips better way. And typically straight carbide is used because that's where you can retain the cutting edge. If you add alloying additions in the carbide, you are not able to maintain the sharp edges, so straight carbide is used. Uncoated, sometimes PVD coated TiO2 kind of coatings are used, which are very hard. So if your material very soft, if you want to cut it good surface finish, the edge need to be sharp, material need to be very hard, so otherwise it will get a tone finish. That's why we go for a hardest coating, PVD coating. And in case where the silicon content is high, you go for a PCD, which is much more productive and gives a good surface finish. And you have avoid built-up edge formation by having a high pressure coolant, and also making it a sharp polished insert. If you polish it, it can avoid the built-up edge formation. And coolant is necessary for chip control, not because of conductivity, it is because of the long and lengthy chips for chip control. Copper and brass is similar to brass and zinc. They're all similar to aluminum, except that your machining parameters are lower compared to aluminum. But rest of the characteristics like tool selection and the coolant, edge preparation are almost similar. So other non-ferrous like rubber, plastic, and composites it's a wide range. It's classified under N5, N6, S7, but each one has a different way of tool selections. But it's something similar. Is you prefer to go with the PCD kind of tools, uncoated carbide with hard coatings, and with a low edge preparation or a sharp edges. It is all three class of non-ferrous material had a similar tool selections and the machining conditions. So the next important material is high temperature alloys. So far we have looked at all material. As you heat it, as the temperature increases, it reduces its properties drastically. Its strength reduces, hardness reduces. It's good for machining because you can apply lower cutting forces. Whereas high temperature material are the one it still have a good strength even at elevated temperature. So that makes it much more difficult to machine. So it's one of the most difficult material to machine, and it is very abrasive. It also reacts with the tool material sometimes, and most commonly used high temperature alloys are either iron based, nickel based, or cobalt based. Okay, so some of the aerospace components and even in the healthcare industry, these components are used, materials are used. So how the selection? So here high strength at elevated temperature, even at during machining, a lot of heat is generated, the strength is much more higher. So you have to apply more cutting forces. Tough and stringy chips, these materials are also ductile, and the strength of the chips are actually harder, they're stronger than the basic material, and resulting more friction on the tool chip interface. Work hardens rapidly. Any material, as I said earlier, high strength, low conductivity tends to work harden, and very abrasive, high cutting forces and temperature generated, and very, very low machinability. The selection, so reduce the cutting force by having a positive rake, make it an insert very positive so that you can reduce the cutting forces. Straight carbide are preferred because straight carbide are having a good toughness and also have a thermal shock resistance because of a strength it required for high temperature application. And PVD coatings are preferred because we want to use a smaller edge preparation. So where we go for a PVD coating, aluminum based coating, ALTAN based coating, run at a very low speed so that heat generation can be limited, reduced, so that work hardening can be avoided. And the use of coolant is a must for these kind of materials so that your work hardening can be eliminated, and also the heat generated during machining is taken away by the coolant instead of transferring to the tool. So similarly, iron based, cobalt based, nickel based, all the material has a similar characteristics. Your tool selection and machining conditions are almost similar. So, okay, so it requires coolant, PVD, sharp edges, straight carbide, positive insert, all are the similar requirements. And the next most important is the titanium alloys used in the aerospace components and nuclear aircraft frames. Medical also is used because of its inertness for the from the individual point of view. In terms of properties, they're tough and stringy. You can see the stress strain diagram. It has a high strength, high ductility, high Young's modulus. It is not so. It will spring back once the load is removed. So it's a tough, stringy chips. Work hardens rapidly. Behavior is similar to superalloys, much more stronger compared to superalloys. Very low thermal conductivity, high chemical reactivity. Titanium reacts with the tool because titanium also one of the tool material, so it reacts. Highly abrasive, cutting forces and temperatures are very high during the machining, and very poor machinability. So it is similar to again superalloys in terms of the selection. High positive incisor require 10 degree, 10 to 15 degree, so that you can reduce the cutting forces. Uncoated is preferred to avoid the reaction and increase the toughness. A very low cutting speed, 50, 60, 70 meters per minute. Built up edge, avoid. You need to have a good chip breaker. I think superalloys and titanium alloys require a good chip breaker to break the chips and take away the chips from the rake interface. Small edge preparation to reduce the cutting forces, and use of a coolant is a must because when the chips are accumulated, it can lead to catching fire. It's flammable. And also, as I shown in the graph here, the Young's modulus is a stress by strain. Is the Young's modulus is very high. Once the load is removed, the tool can spring back. During the machining process, when the portion of the component is machining is complete, it will spring back, can lead to contact with the tool clearance surface, so resulting in rubbing. So you need to create more clearance when you're machining titanium alloys. So the last class of material is the hardened material. It's a similar stainless steel, alloy steel, but you are subjecting heat treatment to get a hardness more than say 48 HRC. And as we discussed in the beginning, that as the hardness increases, your cutting force increases, so a lot of heat is also generated. So these are some of the components, axles, and which is used for heavy duty applications. So it will be very hard. And so there are different hardness categories. So typically the similar cutting tool selection, except for the type of grade used, but otherwise the machining conditions are all on a similar trend. Tough and segmented chips, very short chips because very brittle. The high hardness resulting in high cutting forces, very abrasive tools. It is hardness is maybe almost not exactly close to carbide tooling, but it is the difference is reducing, and which has a very low machinability. The tool selection, the negative inserts are necessary because you saw the previous picture also. It is a negative because the cutting forces are very high, and tool should not break. You need to have a strong insert, so negative inserts. And the PVD coating is preferred to enhance its toughnesses on the carbide inserts or a ceramic or a CBN inserts. Run at a very low speed to avoid the heat generation, reduce the cutting force and reduce the heat generation. So depending on the hardness, if it is the hardness is less than 48 HRC, you go for a ceramic. And when the hardness is more than 48 HRC, you go for a PCBN. So probably a low content PCB and high content PCB, depending on the workpiece material. And watch out for excessive flank wear, and then probably you can have a CBN with the PVD version, coated version, or a ceramic with the coated version. And the use of a coolant is a must, even though they have a fairly good conductivity in some of the tool steel, but the cutting force is so high, a lot of heat is generated, even the component can deform. So to protect the component and protect the tool, so coolant, use of a coolant is a must when you are machining a hard material. So that's all we have for the content. So we spoke about the basic characteristics of the material, and we defined what the machinability means, and we looked into the each material and related to the four characteristics of the material and the selection of a tool in terms of parameters, in terms of a tool material, in terms of a coolant, and in terms of the edge preparation. So this is the basic, and based on your component, so you can optimize the tool selection and machining condition selection. So that's what I have for the content, and I'm open for question. So Isabel, if you have questions in the chat, maybe.
Yes, sure. Great presentation, Ramesh. We have a few questions. The first one is, what properties are desirable in a cutting tool if to perform well in steel, stainless steel, and also super alloys? Can one grade satisfy this need?
Okay, so first thing is the basic requirements in the cutting tool without concerning any workpiece is it should have a high wear resistance. That means when I subject it to a cutting force, it should withstand. Second one is it should have a good toughness or a thermal shock resistance, because during the machining process, there will be interrupted load because I'm using a coolant, and during a coolant, material is heated and cooled, subject to a thermal shock resistance. That means it should have enough toughness. And the third one is on the selection of a right edge condition. So why we mentioned about in one of the variable which we can control is how do I reduce the cutting force, is making the optimizing my edge condition. So for a steel, it's a hardened, high ductile, long chipping material, will have a high strength, and it have a fairly good conductivity. So you might need just a tool which had a nominal cutting edge radius, and when you have a nominal radius, you can have a CVD coating, and you need to have a wear resistant carbide. Moment you migrate from steel to stainless steel become a gummy and work hardening, and can lead to kind of a thermal shock load to carbide can break. So the steel to stainless steel, you need a tougher tool material, and you need to have a chip breaker which are able to handle the stringy long chips. So you need to change the tool material to enhance the toughness, and you need a chip breaker to break the chips. And further you move from stainless steel to super alloys or high temperature alloys, the conductivity of the workpiece is very poor. So that means you need to have a tool which can take care of a lot of heat. And because of the heat and the high cutting forces, it is subject to interrupted or a thermal shock loads. You need a very tough tool. That means you need to further enhance the toughness of the tool, and you move from CVD coating to PVD coating because PVD helps in improving the toughness further. Second, you have to reduce the cutting force for super alloys. So that means I need to have a sharper or a lower edge conditions. Sharp. I don't use the word sharp means zero, maybe 20 micron, 30 micron edge radius, where I cannot use a CVD process. So I go with a PVD tough substrate. So I'm moving from a hard coating, hard substrate to a tough substrate, tough coating as I move from steel to super alloy. So the bottom line is you need to have a different tool material for these three class of workpiece. I hope it's clarifies to a certain extent.
Yeah, let us know if we answer your question or if you have anything else you want to ask. And also, can we share this presentation, Ramesh, because they really enjoyed it. So some people would like to know if you can share it with them.
Should be. Maybe I need to check and I'll come back, Isabel. I'm not sure because some of the contents are general, should not be a problem. But there are some contents are little simulation and all that. I need to check and come back.
Sure. So we will check. Anyway, for all of the people who registered, also the people who could not join, and all of you today, tomorrow you will receive the recording, so you are able to listen to the webinar again. But anyway, we will let you know by email later. We'll take your contact. And another question that we have, Ramesh, is does higher strength aid the chip breaking?
So it's a combination. For example, when you have a super alloys, they have a high strength, but they are not good in chip breaking. So it forms a continue to form a long chipping. It is mainly influenced by the composition, which makes it ductile. So if you have a high strength, low ductile, so it's a good chip breaking. Where you have a high strength and high ductility, it's not a, it require a chip breaker inserts which have a good chip breakability, so to aid the chip breaking. So it is not linearly related. You have both a combination. So I would say that depends on the ductility, the tool selection need to be made whether I need a good chip breaker or not. But typically for a high strength material, it's always recommended to have an insert which are not flat. So you need to have some kind of a rake controlled so that you can reduce the cutting forces. But both require two different chip breaking profiles.
Okay, super. And I wanted to let you know, Ramesh, that we also got some comments that you may be interested in, that the webinar was complete, a good advice, a good refresh on the topics, also that you managed to cover a lot of materials and proper to geometry within an hour. So this was really appreciated. Thank you for all of your comments. We also get a question if we are gonna offer webinars on tool designs offered by WIDIA, like turning inserts and geometry, milling inserts, grade and chip breaker, drills and point geometry versus material. So yes, I will get back to you. I will take your contact and send you some of the webinars that we've already done. I think you will find some of the topics useful. We are also planning, actually we've already planned to do some webinars on some topics that are also related to machinability, and we will show you some examples of WIDIA solutions that we offer for the specific material. So please, as I said before, subscribe to our newsletter. Also, if you're missing the link, I can send it to you. Also to our social media channels, because you will find our next trainings in the next weeks and months, because we have more lined up for you on these topics. We know that machinability is not a topic that we can cover in one session, so we will continue to speak about it also in the future. Let's wait a minute, Ramesh, to see if we have more questions in the meantime.
Sure.
And also remember to answer our survey that you will get at the end, because we really want to know your feedback and comments. We always get your suggestions for the next webinars, and then we make them for you also. So all of your questions are read by us. Okay, great. Anyway, we got a lot of good comments, Ramesh, for a great presentation. So I think we are done with the questions, and we hope to see you in the next session. Thank you for being here today. Have a great day or evening. And thank you, Ramesh, for this presentation. See you soon.
Thank you. Thank you, everyone. Have a good day. Thank you.